For the first time in a while, I think we can just hit straight content for a while, which will probably be good for getting closer to a better place in this class. I'm starting to wonder if we're gonna get to compilers at all this quarter. Class called compilers spends entire quarter talking about the preliminary to compilers. So last time we looked at an NPDA, we talked about NPDA transitions. We built an NPDA for this. We asked about the language that it represents. And if we didn't have this weird rule right here, we just got rid of that, then this would recognize something like A to the N, B to the N. We know this because we start and there's nowhere to transition unless this transition is used if the string is empty. So if N is 0. But if we see an A, then we want to transition over here, saying we found our first A, and we're going to replace the 0 that's on the bottom of the stack with 1 0, showing that now the 1 represents the first A that we've seen. Then we can continue to see A's and add 1s to the stack as long as we see A's. But then we will, on our first B, make a transition, removing A1 on the first B, and then we can sit there and remove a bunch of B's as long as there's a 1 on the stack. If there's a 0 on the stack, that means we have A to the N, B to the N, B something, which is not in the language. So there's no transition defined for that, but that's okay. We'll just terminate in a non-final state and reject. If at some point we see the bottom of the stack character 0, we can only make this lambda transition if the top of the stack is a 0. So if we saw A to the N, B to the N minus something, there were more A's at the beginning than there were B's at the end, then again, we wouldn't be able to make this transition until we'd seen the appropriate number of B's. So now these transitions throughout the graph are limited by what's on top of the stack. So we need to be doing stack peaks. And then the transitions are only allowed if the top of the stack character is what we want it to be to make that transition. So things to know. I think this was all just stated though. Transitions aren't always specified. If a transition is not specified, we reject immediately since there's nowhere for us to go. Then we talked about instantaneous descriptions. We talked about this turnstile character. And we have this triple QWU where we have the first element being the state of the control unit. So which state are we in? What is the current content of the stack? That is the U portion. The W is the unread portion of the string, the entirety of what we haven't parsed yet. So we can use the turnstile to represent one particular state and then another particular state. And the turnstile says we can get from one instantaneous description to another instantaneous description via some transition. We don't have to define what that transition is, but it states that we can, it is provable that we can reach the second instantaneous description from the first instantaneous description. And if that involves multiple transition steps, you want to use a star with the turnstile. So you'll do turnstile superscript star. And that says that through some number of moves, we can get to the second instantaneous description from the first. We feel like we have a basic working understanding of NPDAs and their transitions. All right, let's get an example. Construct an NPDA for the following language. Yeah. The turnstile just says that we can get from one instantaneous description to another instantaneous description via a single move. We don't have to specify what that transition is. But if you see the turnstile star, it says that it is provable to get from one instantaneous description to the next instantaneous description through some number of moves. 0 or more transitions. All right, here's the language. We just care about all strings that have only A's and B's, where the number of A's is equal to the number of B's. If you're stuck on how to start, think about writing a Java program for it that uses a stack. And I think that will help you to be able to construct the NP. Question?
Is there any way to post these slides so I can look back?
At the, yeah,
Okay,
I mean, right now,
I was kind of needing the info.
yeah,
Too, to be honest.
I
okay,
wasn't able to write it down fast enough, so I don't.
gotcha. The instantaneous description.
Yeah, I can take a picture too. Thank you.
Sorry, I tend to go too fast rather than more frequently than too
It's
slow.
okay.
So thank you for asking. That is important. I want to make sure you get the information you need. So first thing you might want to think to yourself, even if just in passing, is this language regular? What do we think? Think it is?
I think I've encountered like this before and it was said to be regular. Maybe I'm misremembering.
How would we generate a DFA for this? What would the states of the DFA represent?
Um, yeah.
Intuitively, in order for this to be regular, we would need to have a state for we've seen an even number of A's and B's. That would be the final state. Then we would need a state that says we've seen one more A than B. We need another state that said we've seen one more B than A. We need another state that says we've seen two more A's than B's. Another state that says we've seen two more B's than A's. Another state that you can imagine that there exist strings out there with an arbitrary number more A's than B's, or an arbitrary number more B's than A's, such that we need some storage in order to keep track of that because it's a variable. There are an infinite number of values for that variable. So because of that, this could not be regular. We could not have a finite number of states that represent an infinite number of states being how many more A's than B's have we seen? So it maps directly onto the number line to the integers. So this language is not regular. But thinking about using a stack, how would you algorithmically use a stack for this problem? It'd be easy if you were recognizing things like all strings with more A's than B's, right? Maybe. Probably not, depends on how it starts. If it starts with more B's than A, then that would be a little bit more difficult. But as long as at any point in the string, there were more A's than B's in the substring starting at the string and going up to that point, then you could always push an A. Whenever you see a B, you pop an A. And there would always be A's on the stack for you to do that. And if at the end of the string, you peaked at the top of the stack and there was an A there, then you knew that you'd seen more A's than B's. What becomes difficult is what happens if at any point we've seen more B's than A's. How do we handle that? There's a fairly simple workaround, but that is the right question to ask. Anyone with some ideas?
Sure, I don't know how right it is.
Let's hear it.
So I have my NPDA has 3 states. It has Q0, which is the final state, Q1 and Q2. From Q0, if it reads an A while the stack has Z, it then pushes an AZ and it's at Q1, which then moves to itself. Q1 then moves to itself, then it reads an A from, and then stack has an capital A, but A on stack. And then also move back to itself on reading B, I wouldn't push anything on to the stack. So it would pop. And then I had with a lambda back to Q0 when it's empty, in case we go from the transition of there's more A's to B's and all of a sudden these A's. In which case it go back to Q0 and then read in a B. I don't know, it's hard to explain.
It sounds pretty close to right. I think though that what we really need is a second stack symbol. We need a stack symbol that represents that we've seen more A's than B's so far, and we need a stack symbol that says we've seen more B's than A's so far. So now this creates 2 cases if we read an A or we read a B. We first peek at the top of the stack and figure out which case we are in. If we see an A and we've seen more A's than B's so far, we want to push a 0. If we've seen more B's than A's and we see an A, then we want to pop a 1. If we see a B and we've seen more A's than B's so far, that means the top of the stack is going to be a 0, then we want to pop that 0. If we see a B and we've seen more B's than A's so far, that means the top of the stack symbol will be a 1, in which case we want to push a 1. Does that make sense? If by the time we finish parsing the string, the stack is empty, the string's in the language. If at the end of reading the string, the stack has either a 0 or a 1, it means that there were either more 0s than 1s or 1s than 0s, which means there were more A's than B's or more B's than A's.
You only need one statement. Because
You need to. You should need at least two states. You need to start, parse, and finish.
Okay.
Because if you have a single state, then it has to be a final state, 'cause at least one string is accepted, right? So you'd accept no matter what, as long as you're in that state.
there's a stipulation that the stack has to be empty to be in the final state or no? To like accept that final.
To accept at a final state, if you make that stipulation, then you could probably do this in fewer
I
states.
thought that was just like part of the. The. NPDAs.
It depends on the definition. If we define that you can lambda transition if the top of the stack symbol is empty to a final state, then you basically get the same thing. So now if we try to draw this as an NPDA. Go ahead and try to finish this off. Take a couple minutes and figure out what the actual transitions are going to be. So let's use the three-state model here, where we have an initial state where we haven't parsed anything. As soon as we see our first character, we're going to transition into a parsing state. Once we finish parsing, we may or may not lambda transition to a final state, depending on what the stack looks like when we get to the end of our string.
Would we want the starting state to be that final state since?
There'll be two final states. Yeah, the start state will be one of them because an empty string has an equal number of A's and B's.
Where you gave that example, I had a solution that was way overcomplicated, but did kind of work.
What was it?
Three states and I used three stack symbols.
Mhm.
Like started with the 0 and then when you go to an A, you push a 1 and then. There's like one state for A's and one state for B's. And if you're in the A, as long as you add an A, you'll keep pushing ones. But then if you go to the B, you'd pop a 1. When you add B's, you push it 2. Then you would pop those 2s if you go back to A and you would just do that.
Transition between those two states, depending on what you see.
And then at any point, if there's the 0 left, you know you have the same amount of number of A's and B's. The 0 that started at the bottom of the stack, you just lambda transition back to the starting state, which was the final state.
Interesting. That would work.
It looks a lot worse than.
Well, it depends on what your definition of worse is. If you think better is fewer states, then yes. If you think better is clearer, you'll see that the middle transition state here has just so many self-references that it's not really easy to read, in which case your solution might be easier to read.
It's very easy to read. There's a lot of errors.
We think we have one? So here we go. Here's a two-state solution. We don't even need necessarily a three-state solution. The three-state solution is more intuitive and kind of brings the lambda transition on an empty out into the initial state. So you can easily do this as a two-state one as well. But the issue is that that Q0 to Q0 loop has 6 possible edges. 6 possible transitions to go from Q0 to Q0. So this very quickly becomes difficult to read. As you can imagine, there aren't too many states, and you stay in the same state as long as you are parsing characters or parsing stack states. And that makes it very difficult to read, which is why we started with grammars. So here's a way to practice the instantaneous descriptions. think about parsing the string BAAB with this NPDA. Go ahead and write the instantaneous descriptions. Who can recall what those three instantaneous description elements were? So if we were to write the first triple here, state remainder of string stack contents, what would it be? What state are we in when we begin? We're looking at this first B. What state are we in?
Q0.
Q0 is where we start. What is the remainder of the string? What haven't we parsed yet? All of it. What is the stack contents? Z, bottom of stack symbol. That's it. So now we can use the turnstile to basically say, okay, moving on to the next one. What is the next description? So what happens from Q0 when we parse a B? Via which possible transition? We have 6 of them with the semicolons here, 1, 2, 3, 4, 5, 6. Which rule are we applying?
Third row, first closest. Yeah. That's the article. Yes.
That one? Yes. So we're going to read a B in our string. The bottom of stack symbol is a Z. So we are going to replace the Z with one Z. So there's a 1 on top of the Z on the stack. So that tells us the next instantaneous description, we're still in Q0. The rest of the string to read is AAB. And the current stack is 1Z. Turnstile. Where do we go from there? We need to parse the A. Which transition are we going to take?
Bottom right.
Bottom right. We want to read an A. The top of stack symbol is a 1. So this says pop the 1, replace it with nothing. So we're still in Q0. We have now read this A, so all that's left is AB. The stack just has a Z on it. Turnstile. What comes next? What transition are we reading?
Second, first row.
We want to read an A. We have a Z on the top of the stack, so we're right here.
Yeah.
We're gonna stay in Q0. We have just a B left, and the stack is going to read 0Z. So there's a 0 on the stack on top of the bottom of stack character. 1. Last one. Actually, there's one more to go. So what happens next? We're gonna read the B. What do we do?
Second on the opposite side.
Now we have a 0 on top of the stack. So we're gonna do this one. We stay in Q0. We have nothing left to read. And we have the bottom of stack symbol. Note that now we are in a state that we can use this transition on. We can make a lambda transition that doesn't consume any characters because there aren't any characters left to consume. There needs to be a Z on the top of the stack. The bottom of the stack character needs to be on the bottom of the stack in order to be able to do this. But that's the state that we are in. So we can see that we, via instantaneous descriptions, can transition to Q1. There's still nothing left to read, and there's nothing on the stack. But this is the final state, so we accept. We're done parsing the string, and we've reached a final state. Because those two things are true, we can accept the string. So this is the kind of process that we will want to go through if we are reading an NPDA. Those instantaneous descriptions are very nice, and they show you exactly what the process is. It's very much like writing out the sequence of states that you visit in a DFA or an NFA. I go from this state to this state to this state, but that's all the information you needed. Now we need to keep track of the stack contents as well. So this instantaneous description form it's very easy to spot mistakes in it. Because from each turnstile, we should be removing the first character of the string or making a lambda transition.
So something I'm still not getting is, why are we popping the leftmost character and not the rightmost character?
Because we start reading from left to right. You mean in the string
Yeah,
or in the stack?
because sometimes we read right to left, right? Where it's like you pop the rightmost, or am I misremembering?
Are you thinking of just a stack in general?
Yeah.
This is the stack. This is just the way that this is written. You could completely reverse the process. A stack doesn't really matter which direction it's pointing, but we think of our stack kind of as pointing in this way, where the top element is on the left and the bottom character is on the right. It very well could be that you write a stack the opposite way, but the way that the textbook does it, so the way that we'll do it in the class is that we'll do it this way.
Just to add on to what he was saying, I think before you might have thought we were talking about like the string that you were taking.
Yeah, I guess I meant more the string.
But it's the stack that you're thinking about that we pop from like, that we look at the things on the right side and then.
Okay, maybe that's what I'm mixed up.
Yeah, with regards to the string, we parse the string from left to right. There's no way to parse the string from right to left easily and determine whether or not it's in the language. I mean, I guess you could start at the final state and undo everything, like reverse the arrow. Starting, assuming you're in a final state, you work your way back to the start state. But then if there are multiple final states, then you'd have to start at each possible final state and see if there exists a single path for you to work back to the start state. So it's much easier to start from the singular start state and work your way to see if you end up in any of the final states, because you can do that with one pass over the string.
I guess also, what I just spoke into for that, to read the fourth transition. In our work, the second row on the right, where it has 0Z. How do we take things off of the stack on that one? I don't remember if it was from left to right or right to left, as far as like how we looked at it.
From here to here.
Yeah. Do we take the 0 off?
Yeah, this transition that we did, reading a B. We go from there being a 0 on the stack to removing that 0. So this says, remove the 0, replace it with nothing.
So I think we're just having a little bit of like mechanical confusion of
Yeah.
moving things, but I guess if this is how it goes, then that.
So we remove the 0 and replace it with nothing. Removing the 0 just means that the Z is on top.
Yeah.
So yeah, we never push lambdas. Lambdas are like the empty string or the nothing. So lambda just basically says don't do something in this case. Other questions, clarifications? They're over here. Yeah, so I totally drew these the wrong way. Turnstiles can kind of go either way, but I guess the bar is supposed to go to the right, so that's what I just drew out. If we end in any accepting state or final state with an empty stack, then we accept the input string. So yes, the stack must be empty as part of the acceptance criteria. Does that make sense? That is an important distinction for people. You can't just end in a final state. You have to end in a final state with an empty stack. Here's another one. Our good old friend WWR. Is this language regular? It was not regular. So as always, you can think about how would you proceed to parse this algorithmically? Thinking that you have a stack.
Just a question about the notation. What is
Yeah.
the plus meant to be in this?
Plus means one or more. So it's the positive close.
Oh, that's right.
Yeah, so we can't have an empty string and have that be recognized as, hey, it's a palindrome.
Forgot what it was. Yes, start. Minus this.
Yeah. Can you, instead of like having thing, like when you read an A and the stack is empty, you. Can you just say like when you read an A, no matter what state the stack is in, you just push?
Yeah.
As you go? Okay. Is there a way to write that, or is it just?
You could write. You would technically need a rule for the peak, like the top of the stack is A. So you would need to write,
Well, it doesn't matter what the top of the stack is, I just want to push when I read an A.
yeah, you'd still need a transition for every possible top of the stack. But yeah, this is why the language for NPDAs is really annoying, because think about it algorithmically, you would need to say. There's no way for a computer to recognize if there's any character.
So I only have to write one line.
Yeah. Remember that this is non-deterministic, so you're not constrained by determinism. So if you're asking the question, like, how do I know when we're transitioning from W to WR? You don't need to. Wherever that happens to be, that is where it will do it.
I don't like that. Because say you're parsing through it and you get to some point. And then you transition, but say you transition to too late, it's just like, oh, now I.
Remember that instead of a single transition, you're branching and doing multiple transitions at the same time. So think of it like parallelism where you have infinite CPUs.
Yeah, because just like realistically parsing, you have to try doing like.
Yes.
Switching from W to WR every single.
Absolutely. And the reason I give you this example is because it turns out that unlike how DFAs and NFAs represented the same class of languages, NPDAs and DPDAs represent different classes of languages. And only NPDAs are equivalent to context-free languages.
Can you do something where like, there's kind of pre-work of just pages, push W, the first half button to the stack. And then start the state, like the processing.
I think you want transitions for each possibility there. So if you're in a state and you're still in the process of pushing W, then if you see an A, push whatever stack symbol represents that you've seen an A. If you see a B, push whatever stack symbol is for seeing a B, and eventually you will just lambda transition over to, all right, we've seen W, now we're gonna start recognizing WR. Non-determinism is fun, isn't it?
No, it's not.
We're all primed to think deterministically, so thinking non-deterministically just feels weird. You have infinite parallelism at your hands.
I can't determine if I like it or not.
Can you non-determine if you like it or not? The answer is yes, there exists a way for you to like this, so you're going to like it now.
But maybe there doesn't exist a way for me to like it.
With the infinite possibilities of learning non-determinism, there has to be. Here's some language on the slide that defines what we just talked about, the fact that we don't really need to care about where the middle of the string is. If there exists a middle such that a palindrome can be found, then we will handle by non-determinism. If there is in any such middle position in the string that leads to a palindrome, we will find it, and it will lead to a final state. So here are the different classes of transition rules that we're going to need. I like to think about whenever I'm making an NPDA, I like to think about trying to break the transition rules down into their associated classes or steps, algorithmic steps. So think about the problem algorithmically. We need to push all characters from W onto the stack. Then we need to pop all characters from WR off the stack. So we will need some set of rules for pushing the string onto the stack. We will need some rule for guessing where the middle of the stack is going to be. And we need to be able to match against the reverse. And then we need to be able to recognize when we have completed the process. So if we're at the end of the string, we need some way to accept if it is a palindrome and to reject if it is not a palindrome. How are we doing? Do we have something approaching a solution? How do we, where are we in the process?
States. Wait, just in my head. You know, if you should block, just. Whatever it's called. Yeah. Well, that's what we okay.
All right, what rules do we have for pushing the string onto the stack? What transition rules do we need?
We need 6 of them.
So we need some way to be in our initial state when we start and read the first character being an A. Great. If we do that, then we want to pop and push. And that's if an A is on the top of the stack. If we see a B and an A is on the top of the stack, then we need to push the B on top of the A. If we see an A and a B is on top of the stack, we need to push the A. If we see a B and a B is on top of the stack, we need to push the B. And we need 2 rules now for the bottom of the stack character. So if the bottom of the stack is the bottom of the stack character, then we see an A, we need to push an A. And if we see a B, we need to push a B. This gives us all of the rules for how to do this, and none of these involve any state transitions whatsoever because they don't change the internal representation of what we are doing, what step in the algorithm we are in. We are still pushing W onto the stack. So this is one easy way to break NPDAs down into states. You can think about breaking the process down into methods. And each method is going to be a state, where you have some repetitive process that says, for each symbol in W, push W onto the stack. There's going to be a state that represents that's where we are in the algorithmic process. We need something for guessing the middle of the string. What are those going to look like?
Transition.
Lambda transitions?
There's an A, you pop and then push an A. There's a B, you pop and then push a B.
Yep.
So just leave it the same.
So these are lambda transitions that basically say, make no change to the top of the stack. Because when you make one of these transitions, you must pop. This basically says this is the no op rule that says that you're going to pop and push the same character. So this is why we need 2 of these transitions, is because it does matter what character is on the top of the string, and the 2 rules say you do the same thing regardless of what's on the top of the string. Top of the stack. I can speak. Rules for matching. This W unsuperscripted R against the stack. Gets to that. What are these rules? How do we start recognizing the reverse? Yep. Only need those two rules, right? If we're in the reverse and we see an A, and there's an A on top of the stack, then we can get rid of it. If we read a B and there's a B on top of the stack, we can get rid of it. What happens if we read an A and there's a B on top of the stack? Yeah, you reject right then and there. Now note that there's a lot of parallelism going on here. If we were to describe this process, like let's say we have a string that's actually a palindrome. We'll make this as simple as possible. B, A, B. Here we have a palindrome. We would, in one sense of this parallelism, we would push the B on the stack, and that would be the entirety of W. Then we would lambda transition over to saying, can we pop AAB from this stack? And we'll see a mismatch between this A and the character that's on top of the stack. So we reject this at this point. But in parallel, we are doing B A lambda transition. And we need to map this against AB, and we see that this is going to lead to success. So non-determinism is absolutely guessing where the middle of the string is, but it's going to consider every possible middle of the string. So this is going to be able to match the A to the A and the B to the B, which will lead us to basically an empty string where we get to accept. Meanwhile, it's also in parallel going to be looking at, it's going to push B, A, lambda transition, and try to map just the last B against B, A. This will lead to failure. And in parallel, it will be pushing B, B onto the stack, lambda transitioning and trying to map this B, B to the empty string. And that's going to fail. So when we say that it's guessing where the middle of the string is, what we're really saying is there such a middle such that one of these or more of these end in success? In this case, you can't have two possible middles of a string where you have a palindrome. There will only be 1 or 0. But if there exists one, this parallel process will find it. You can think of all of these running in parallel, where the first step of this is push B. The first step of this is push B, push B, push B. These all started out with the same step. But then this one's second step is to transition. It's going to transition to Q1. This one's second step is to push A, push A, push A. This one's third step is to map this A to this B and reject. This one's third step is to lambda transition over to Q1. This one's third step is to push A and push A. So they're all working in parallel for each step. But if one of them happens to succeed, then we accept. And this happens to be the middle of the string. There exists some such middle of the string such that we have a palindrome. And of course, with longer strings, there would be more of this happening in parallel. That's non-determinism. Does that make sense? Questions about this? Thank you. There's the last rule. So there's the acceptance rule. I'll just leave you with a full solution so you can go analyze it if you want to. We'll come back tomorrow and start thinking about how we can convert context-free grammars into non-deterministic pushdown automata. I couldn't remember for the life of me how I was reading strings. Remember, you have an assignment due tonight. I am heading over to my office for a couple hours of office hours. Welcome to join me.
Questions. You know that.